Well, we're basically skipping section 5 about the uniqueness and existence of the first order differential equation with initial condition, but let me say something real quickly about it. We saw in section 3 that it looks like any first order differential equation y prime equals f of t and y with an initial condition y of 0 equals something is surely going to have a unique solution, because you can just follow, start at the given point, follow the slope field, and what could go wrong? There's only one way to follow the slope field, it seems. Of course, for different initial conditions, you get different solutions, but once you've pinned down the initial condition, it looks like you should always get one and only one solution. And that's almost true. Section 5 basically says that's true unless there's something weird about the right-hand side function f. And here's an example. It's actually the same as the example given in the text that shows how something could go wrong. Look at this differential equation, y prime equals 3y to the 2/3 power. There's actually 2 with y of 0 equals 0. You can easily check that there's 2 different solutions, and surprisingly exactly 2, not an infinite number, but y equals constant 0 is obviously a solution because the derivative of 0 is 0 and 0 to 2/3 is 0, so it satisfies the differential equation, and y of anything is 0, so it satisfies the initial condition. But so does function t cubed, because what is y prime? It's 3t squared. What is y to the 2/3? If y is t cubed, that's t squared times 3, so 3t squared equals 3t squared, so it also satisfies the differential equation. When t equals 0, y is 0, so 2 different solutions to the same differential equation with the same initial condition, and we just said that should never happen. But actually, the only way it can happen, according to the theorem in section 1.5, is if the partial of f, that is the right-hand side, with respect to y, is not continuous at the initial point. Well, that is the case here, because you take the derivative of 3y to the 2/3, and what do you get? You get 2 times y to the minus 1/3. That means 2 over the cube root of y, and when y is 0, that's infinite. So that's one of those weird functions. Rarely happens in real-world applications. So basically, it's y prime equals f of t and y with the y of 0 equals something is almost always going to have one and only one solution. In section 1.6, equilibrium and the phase line, well, all of chapter 1 is about the first order differential equation y prime equals f of t and y. But section 1.6 is specifically about autonomous equations where the right-hand side is a function of y only. No t on the right-hand side, this whole section. Now, if the right-hand side is a function of y only, then we can identify equilibrium values of y, that is, values of y for which f of y is 0 and y doesn't change. So if y starts out at a value such that f of y is 0, then y will stay the same forever. For example, the equation y prime equals 1 minus y times y, that's autonomous. And by the way, autonomous problems are always separable, so in theory you can solve them using separation of variables, but only if you can do the antiderivatives, and in our problems they're usually very hard, involving partial fractions, or impossible, so we're not going to try to solve them even. But we can qualitatively analyze, and that's the point. For the autonomous problems where the right-hand side is a function of y only, such, for example, 1 minus y times y, logistic equation, we can analyze things qualitatively fairly easily. First, you can find equilibrium points. Those are values of y for which the right-hand side is 0, namely, in this case, y is 0 or y equals 1. So if you start at y equals 0 or y equals 1, you'll stay there because y prime will be 0 forever. So those are called equilibrium points, 1 and 0. Now, for an autonomous problem, remember, that means the right-hand side is a function of y only. That means as you go left and right on t, the slope field doesn't change. So here's the slope field for this equation, and for any y, the slope doesn't change with t, doesn't change as you go left or right. So we draw something called a phase line. See, there's really no point in drawing the whole slope field here because it's the same for all t for a given y. It only depends on y. So the phase line is kind of a shorthand notation for the slope field for autonomous problem, and it shows the equilibrium points with little dots there. That means if you start at a dot, you'll stay there. And in between, there are arrows showing whether it goes up or down. The arrows don't try to show how steep they're going up or down, just are they going up or down. So if you look at the slope field, you can see, well, kind of hard to see here, but it's barely positive. So if y is between these two equilibrium points, y prime is positive. So if y is between 1 and 0, those are both positive, so you're going to get positive. If you're above y equals 1, slope field is downward, so you draw an arrow going down. If you're below 0, it's also going down. So this little phase line is kind of an abbreviation for the whole slope field. In the case of an autonomous problem, it just shows that if you're anywhere between here and here, you're going to go up. If you're above that, you're going down. If you're below that, you're going down. And that tells you a whole lot about qualitatively what happens to solutions. If you start anywhere between here and here, you're going up, and you're going to get closer and closer to this equilibrium point. You can't ever pass it. You're going to keep going up until you get closer and closer to that equilibrium point. You can't pass it because if you ever got to the equilibrium point, you'd be stuck there. So you can't cross the equilibrium point, but you're going to get closer and closer to it. So if you start at any point here, you're going to converge to that. If you start above it, you're going down, and you can't go past the equilibrium point, so you go down to the equilibrium point asymptotically. If you start below this, you're going to go down, and you can go on down forever. So this problem has two nodes, and this node y equals 1 is called a sink because it sucks solutions into it. So if you start above or below, you get sucked into that equilibrium point. Above, you're going down. Below, you're going up. So this is a sink. This is called a source. We'll see in the two-dimensional problem why they're called sinks and source, but a sink is basically it's sucking the water into that equilibrium point. The source, it's blowing water out of it. So if you start close, if you start exactly at y equals 0, you'll stay there forever. But if you start a little bit above or a little bit below, you're going to get blown away from it. So that's called a source. So we have equilibrium points, and we can classify the equilibrium points as sources or sinks. Sink if solutions real close to the equilibrium point get sucked into it. Source if they get blown away. But what if an equilibrium point is a source on one side and a sink on the other? For example, here this differential equation, you can see that it's autonomous. There's no t on the right-hand side. Equilibrium points, the only one is y equals -1. When y is -1, y prime is 0, so you stay there. So if you start at -1, you'll stay there exactly. But what happens if you start a little above? Well, you get blown away. See, this is positive. Y prime is 0 when y is -1, and it's positive for any other y. So you're going up whether you're above or below. So if you start a little bit above, you get blown away. If you start a little below, you get sucked in. So it's kind of half sink below and a source above, and that's called a node. So equilibrium points you find by setting the right-hand side equal to 0 and solving for y. And each equilibrium point can either be a sink if it's blown away on both sides, a source. It's a source if it's blown away on both sides, sinks if it's sucked in on both sides, and a node if it's sink on one side and source on the other. And DE Tools has an app for that, of course. Here I've got the menu set on the logistic equation. When a is 0, so ignore the a. So it's just y prime equals y times 1 minus y, the equation we were just analyzing. And as we saw there, we have two equilibrium points. If y is 0 or 1, the right-hand side is 0, so we have two equilibrium points. And here's the slope field. And see, if you're between 0 and 1, you're going up. If you're above 1, you're going down. If you're below 0, you're going down. So this is a sink. You start a little above or below and you get sucked into it. 0 is a source. You start a tiny bit above or below. You get blown away. It's kind of like, this is like the top of a mountain. If you start stand exactly on the top of the mountain, you'll stay there, but if you go a little bit one side or the other, you'll roll down it. This is like the bottom of a valley. You start on either side and you get sucked back into the valley. Okay, let's look at the homework problems in section 1.6. For example, problem 2, that's autonomous because there's no t on the right hand side. You factor that and find the equilibrium points, and you need to draw the phase line, basically draw the equilibrium points, and between each equilibrium point, see that it's either going to be going up everywhere between two equilibrium points or going down. It can't change from up to down unless it passes through an equilibrium point. So just pick a point between the equilibrium points, or above the top one or below the bottom one, and see whether y prime is positive or negative. So draw the slope field. Once you have the slope field drawn, you can answer the questions, the next questions, which say if you start at 1, doesn't matter what t is actually, if you start at 1, what's going to happen? Well, look at your phase line and look at 1 and see, are you going up or down? And if you're going up, you go up until the next equilibrium point. If you're going down, you go down to the next equilibrium point and you can't pass it. So you can figure out what's going to happen to y for each of these 4 different cases, no matter what, no matter if it's impossible to solve the differential equation. You can qualitatively tell what happens to solutions. And the homework or test problems are easiest if they're matching. It's like this problem 37 that I gave you. There are 4 phase lines. Again, remember, these phase lines are basically just shorthand for the slope field, since the slope, if it's down here, it's down for all t for that y. If it's up here, it's up for all t for that y. So it's an abbreviated form of the slope field. And you're supposed to identify which of these differential equations could have that phase line by elimination. And there's a number of ways of doing this, but let's look at A. You can see that there are equilibrium points at 0 and 1. So first look for which of these 8 have equilibrium points at 0 and 1 only. And the ones with cosines and sines are going to have an infinite number of equilibrium points. So forget those. So it has to be one of these 4. And this factors is y times 1 minus y. That's y times y minus 1. This you factor out a y squared times y minus 1. That's y squared times 1 minus y. So all 4 of those have the right equilibrium points, so 0 and 1. But for the phase line here, you can see that y equals 0 is a node because it's going up below it and up above it. So it's like a source above and a sink below. So y equals 0 is a node, whereas y equals 1 is a sink. So which of these would have y equals 0 as a node? Well, neither of these will, because those factors y times something, and the y changes when y goes from below 0 to above 0. Y changes sign, but here they have a factor of y squared, which doesn't change when you go from below to above. So if this is y squared times y minus 1, the y squared is 0 and y is 0, but it doesn't change as you go slightly above, slightly below. It doesn't change. So these two have, so all 4 of these have the right equilibrium points. These 2 have the right equilibrium points, and y equals 0 is a node. But which one of these is it? Well, you can maybe the easiest thing is just pick a value here to where you get different right-hand sides. Say y equals minus 1. Y equals minus 1, that would be a minus 1, that's negative, whereas this is positive, minus negative is positive. So this one predicts that y prime is positive when y is minus 1, which is the case. You can see when y is minus 1, it is indeed positive, not negative, so it must be 8. And going back to this problem here where you had a node at y equals minus 1, it's the square that makes it the node here, because see, this is squared. It means it's not going to change sign when y goes from a little bit below minus 1 to a little bit above. It's going to stay positive, which means it's going up above and below, so it can't be a sink or a source. It has to be a node. So you can usually identify nodes by factors that are squared or even powers.